The 5-day countdown. 5 days from now, something will happen that has not occurred in recorded human history. An object born around a star that died before our sun even existed will reach its closest point to Earth. And in the last 72 hours, the data coming back from our most powerful observatories has changed everything we thought we knew about 3I-ATLAS. Tonight, I am going to walk you through what the scientists are not telling the public. Why the European Space Agency just released the first ever X-ray image of an interstellar visitor. Why this ancient traveller has changed colour 3 times since August. Why it is producing a chemical signature that breaks every model we have for cometary behaviour. And why one of the most controversial astrophysicists at Harvard believes with 30 to 40% certainty that we are not looking at a comet at all. By the end of this documentary, you will understand why December 19th, 2025 may be remembered as one of the most important dates in the history of astronomy, or why it might fade into obscurity like so many other cosmic near-misses. The truth is, we do not know yet, and that uncertainty is precisely what makes this moment so extraordinary. Before we begin, make sure to like and subscribe if you enjoy these topics. It really helps the channel. The date is December 14th, 2025. As I record these words, 3I-ATLAS is hurtling through the inner solar system at approximately 250,000 kilometers per hour. That is among the fastest velocities ever recorded for any object passing through our cosmic neighborhood. To put that into perspective, if you could somehow hitch a ride on this interstellar wanderer, you would travel from New York to Los Angeles in about 40 seconds, from Earth to the Moon in roughly 90 minutes. This is not the lazy drift of an asteroid caught in the sun's gravity. This is the desperate velocity of something that does not belong here. Something that is just passing through. 5 days from now, on December 19th, this ancient visitor will reach what astronomers call its closest approach to Earth. It will still be far away by any human standard. Approximately 270 million kilometers. That is roughly 1.8 times the distance between our planet and the Sun. You could fit about 700 Earths in that gap. So no, this is not a disaster movie scenario. 3I-ATLAS poses absolutely no threat to our planet. NASA has made this abundantly clear in statement after statement. But proximity is relative when you're talking about objects from other star systems. Consider that the nearest star to our Sun is Proxima Centauri at roughly 4.2 light-years away. 3I-ATLAS has travelled that distance and more to reach us. It has drifted through the absolute darkness of interstellar space for billions of years. And now, for a brief cosmic moment, it is close enough for us to study with instruments that did not exist even 20 years ago. What makes this encounter extraordinary is not just the distance, but the timing. December 19th falls on a new moon. For astronomers, this is the equivalent of Christmas morning. The absence of moonlight means darker skies. Darker skies mean clearer observations. It is as if the universe itself is offering us the optimal conditions to witness this visitor during its closest pass. Hundreds of observatories around the world are preparing for that night. The Hubble Space Telescope has already turned its gaze toward 3I-ATLAS multiple times, and will do so again. The James Webb Space Telescope continues its analysis. Ground-based facilities from Chile to Hawaii to the Canary Islands are coordinating their efforts. We have never thrown this much observational firepower at a single object in such a compressed time frame, but here is where the story takes its first unexpected turn. The data coming back is not matching our predictions. Let me be precise about what I mean by that. When 3I-ATLAS was first discovered on July 1st, 2025 by the Atlas Survey Telescope in Chile, astronomers immediately recognized it as something special. Its trajectory was wrong. Not wrong in the sense of dangerous, wrong in the sense of impossible for any object born in our solar system. It was moving on what we call a hyperbolic orbit, a path so extreme that our sun's gravity cannot hold it. This object came from somewhere else, it is going somewhere else, and we happened to be in its path for a few precious months. Now we have seen interstellar visitors before. The first was Oumuamua in 2017, a strange elongated object that sparked intense debate about whether it might be artificial. The second was Borisov in 2019, a more conventional-looking comet that behaved more or less as expected. 3I-ATLAS is the third, hence the 3 in its designation. The I stands for interstellar, and from the moment of its discovery, scientists assumed it would follow a familiar pattern. It would approach the Sun. It would heat up. It would release gases and dust in predictable ways. It would develop the characteristic tails that define cometary behavior, and then it would disappear back into the darkness from which it came. For the first few months, this is exactly what appeared to happen. The Hubble Space Telescope captured images showing a teardrop-shaped coma, that fuzzy envelope of gas and dust that surrounds a comet's solid nucleus. The James Webb Space Telescope detected carbon dioxide, water, vapor, water, ice, carbon monoxide, and carbonyl sulfide. All the usual suspects for a comet being warmed by stellar radiation. Everything seemed normal, different from our local comets certainly, but recognisably cometary in nature. Then 3I-ATLAS did something that broke the model. In late October, the comet reached perihelion, its closest approach to the Sun at about 203 million kilometres. This is the moment when comets typically become most active. The intense solar radiation should have triggered massive outgassing. We expected to see a spectacular tail streaming away from the Sun. We expected brightness increases following well-understood patterns. We expected 3I-ATLAS to behave like every other comet that has ever swung close to our star. Instead, it went quiet, or at least quieter than the models predicted. Post-perihelion images released in early November showed what astronomers described as a compact source of light without a clear cometary tail. The coma was there, but it looked almost unchanged from months earlier. This was strange. Very strange. If 3I-ATLAS was a typical icy body losing mass through sublimation, it should have shown dramatic changes after its solar encounter. The absence of those changes sent a ripple of confusion through the astronomical community. Now, I need to be careful here because this is where the line between science and speculation becomes dangerously thin. The mainstream explanation for this behaviour is straightforward. 3I-ATLAS is simply different. It formed in another star system under different conditions. Its composition is not identical to our local comets. Its ice content, its dust ratios, its internal structure, all of these variables could explain why it does not behave exactly as predicted. This is the conservative interpretation, and in science, conservative interpretations deserve the benefit of the doubt. But there is another interpretation, one championed most vocally by Avi Loeb, the former chair of Harvard's astronomy department, and current head of the Galileo project. Loeb has been tracking 3I-ATLAS since its discovery. He has catalogued what he calls anomalies, behaviours and characteristics that do not fit neatly into the natural comet explanation. As of his most recent count, there are 10 such anomalies, and while Loeb is careful to state that 3I-ATLAS is most likely a natural object, he assigns a 30 to 40% probability that it may have a technological origin. Let that sink in for a moment. One of the most credentialed astronomers in the world is suggesting there is roughly a 1 in 3 chance that the object approaching Earth right now is not entirely natural. He is not saying it is an alien spacecraft. He is saying we cannot rule that possibility out with the data we currently have. And he is calling for more observation, more analysis, and more willingness to consider explanations that fall outside our comfort zone. The response from the scientific establishment has been predictable. Most planetary scientists have dismissed Loeb's suggestions as sensationalism. They point out that unusual does not mean artificial, that our models for interstellar comets are based on exactly 2 previous examples, that the strange behaviours Loeb highlights can all be explained through natural processes we simply have not encountered before. Jason Wright, an astronomer at Penn State, has written detailed rebuttals, cataloguing how each of Loeb's anomalies can be understood within conventional physics. This debate matters because it reflects a deeper tension in how we approach the unknown. Do we assume the simplest explanation until forced to consider alternatives? Or do we keep our minds open to possibilities that might transform our understanding of the universe? Both approaches have value, both have risks, and 3I-ATLAS is testing the limits of both. What I find most compelling about the current moment is not the debate itself, but the data that continues to pour in. Every day brings new observations, new measurements, new puzzles. In the last 72 hours alone, we have received X-ray images from the European Space Agency's XMM Newton Observatory. We have seen colour changes documented by the Gemini North Telescope in Hawaii. We have learned about chemical signatures that challenge everything we thought we knew about cometary composition. Each piece of evidence adds texture to our understanding, and each piece raises new questions. This is why the next 5 days matter so much. December 19th is not just the closest approach, It is our best opportunity to gather the high-resolution data that might finally settle the debate. After that, 3I-ATLAS will begin its long journey toward Jupiter, arriving near the gas giant in March of 2026. And then it will disappear. Forever. We will never see this object again. Whatever secrets it carries will vanish with it into the interstellar void. So what do we actually know? What has the latest science revealed? And why are some researchers more unsettled now than they were 6 months ago? The answers begin with something we could not see until 12 days ago. The invisible light that 3I-ATLAS is emitting. X-rays streaming from an object that should not produce them. At least not in the quantities we are detecting. When X-rays revealed the invisible. On December 3rd, 2025, the European Space Agency pointed one of humanity's most sensitive instruments at 3I-ATLAS. The XMM Newton Observatory is not your typical telescope. It does not capture the light we see with our eyes. It does not photograph the visible spectrum that paints the universe in familiar colours. Instead, it detects X-rays, the high-energy radiation that passes through flesh and bone, the kind of light that requires extreme conditions to produce, temperatures of millions of degrees, violent collisions between particles, the death throes of stars. X-rays are the fingerprints of the universe's most energetic processes. And for 20 hours straight, XMM Newton watched 3I-ATLAS glow in a light that should have been impossible to see. The image released on December the 12th shows something remarkable. At the centre, a bright red spot stands out against the absolute darkness of space. This is the comet's X-ray emission rendered in false colour, so human eyes can perceive what would otherwise be invisible. Surrounding this core, faint gradients of purple and blue spread outward, like ripples in a cosmic pond. The red represents low-energy X-rays. The blue marks the void where almost no X-rays exist. Between them lies the boundary between something extraordinary and nothing at all. Now you might be wondering why this matters. Comets are balls of ice and rock. They are cold objects heated only by the distant warmth of passing stars. How could something so fundamentally frozen produce radiation associated with stellar furnaces and black hole accretion disks? The answer lies in a process called charge exchange, and understanding it reveals something profound about how 3I-ATLAS is interacting with our solar system. As 3I-ATLAS moves through space, it releases gas. Water vapor, carbon dioxide, methanol, and other volatile compounds sublimate from its surface and stream outward, forming the coma we observe in visible light. This gas is electrically neutral. Its atoms and molecules carry no net charge. They're just drifting particles expanding into the vacuum. But the space between planets is not truly empty. It is filled with the solar wind, a constant stream of charged particles flowing outward from the sun at speeds of several hundred kilometers per second. Protons, electrons, ionized atoms of heavier elements. This wind carries the sun's magnetic field throughout the solar system, and when it encounters the neutral gas streaming from a comet, something violent happens. The charged particles in the solar wind collide with the neutral gas molecules surrounding 3I-ATLAS. During these collisions, electrons are exchanged. The solar wind ions capture electrons from the cometary gas, and as these newly captured electrons settle into their new atomic homes, they release energy. X-ray energy. It is like a cosmic game of musical chairs where each time someone finds a seat, a burst of high-energy light escapes into space. This process happens billions upon billions of times, creating a diffuse glow of X-rays that extends far beyond the visible coma. This phenomenon is not unique to 3I-ATLAS. Astronomers have observed X-ray emission from solar system comets before. Comet Hyakutake in 1996 was the first to be detected in X-rays, and the discovery surprised everyone at the time. Since then, we have learned that charge exchange is a common feature of cometary environments. So in one sense, the XMM Newton detection simply confirms that 3I-ATLAS behaves like a normal comet. It releases gas. That gas interacts with the solar wind. X-rays are produced. The physics works exactly as predicted. But here is where the observation becomes more interesting. The intensity and extent of the X-ray emission can tell us things about the comet that optical telescopes cannot. X-rays are particularly sensitive to certain gases that are nearly invisible in other wavelengths, molecular hydrogen, molecular nitrogen. These species do not produce strong signatures in visible or infrared light, but they participate enthusiastically in charge exchange reactions. By analysing the X-ray spectrum, astronomers can probe the hidden chemistry of 3I-ATLAS. They can search for molecules that other instruments might miss entirely. The XMM Newton observation lasted 20 hours. During that time, 3I-ATLAS was approximately 282 to 285 million kilometres from the spacecraft. The European Space Agency used its most sensitive X-ray camera called EPIC-PN to gather every photon it could. And the preliminary results suggest something worth paying attention to. The spectrum shows excess emission components associated with carbon, nitrogen and oxygen. These are exactly the elements you would expect from charge exchange between solar wind ions and cometary gas. But the relative intensities of these emissions contain information about the gas composition, information that scientists are still working to decode. Less than a week before XMM Newton made its observations, another X-ray telescope had already turned its attention to 3I-ATLAS. The Japanese Aerospace Exploration Agency operates a mission called XRISM, the X-ray Imaging and Spectroscopy Mission. From November 26th to November 28th, RISM conducted what astronomers call a target of opportunity observation. This means they interrupted their normal schedule specifically to capture data on an object of exceptional interest. For 17 hours, the satellite tracked 3I-ATLAS as it drifted through the constellation Virgo. The spacecraft adjusted its altitude 14 times over those 17 hours. Every 3 hours, it repositioned itself to keep the interstellar visitor centered in its field of view. What XRISM found added another layer to the mystery. A faint X-ray glow extending approximately 5 arc minutes from the comet's position. In terms of actual distance, that corresponds to roughly 400,000 kilometers. Think about that for a moment. The X-ray halo surrounding 3I-ATLAS spans a volume of space larger than the distance from Earth to the Moon. This is not a compact point source. This is an extended structure, a vast invisible cloud of interaction between an object from another star system and the charged wind flowing from our Sun. The XRISM team was careful to note that their results are preliminary. Instrumental effects can sometimes mimic extended structures, and careful analysis is required to separate real signal from artifact. But even with those caveats, the detection is significant. It suggests that 3I-ATLAS is actively outgassing substantial quantities of material that extends far beyond what we can see in visible light, material that may contain clues about the comet's origin, composition and history. Avi Loeb was quick to comment on these X-ray observations. In a blog post published shortly after the XRISM results became available, he noted that the X-ray halo appears consistent with the gas plume detected earlier by NASA's Sphere-X observatory and the James Webb Space Telescope. This is actually a point in favour of the natural comet interpretation. If 3I-ATLAS was some kind of artificial object, you might expect its X-ray signature to differ dramatically from natural comets. Instead, it seems to be doing exactly what a comet should do, releasing gas, interacting with the solar wind, producing charge exchange X-rays in predictable ways. But Loeb also raised a question that cuts to the heart of the ongoing debate. We are seeing what happens when cometary gas meets the solar wind, but we are not directly imaging the source of that gas. The nucleus of 3I-ATLAS remains too small and too distant to resolve clearly even with our best telescopes. We see the effects of outgassing. We do not see the outgassing mechanism itself, and that leaves room for interpretations that go beyond the conventional. Consider an analogy. Imagine you're standing on a hillside watching a distant factory. You can see smoke rising from the chimney. You can measure the composition of that smoke as it drifts on the wind. You can calculate how much material is being released based on the density and extent of the plume. All of this tells you that something is burning inside the factory, but it does not tell you what that something is. Is it coal, natural gas, wood, industrial waste? The smoke alone cannot answer that question. You would need to get closer. You would need to see inside the furnace itself. 3I-ATLAS presents us with a similar challenge. The X-ray observations confirm that gas is streaming away from the nucleus and interacting with its environment. They tell us the approximate composition of that gas based on the spectral signatures, but they do not tell us the fundamental nature of the object producing that gas. Is it a pristine ball of ice and rock unchanged since its formation billions of years ago around another star? Is it a processed remnant altered by cosmic ray bombardment and stellar radiation during its journey through interstellar space? Or is it something else entirely? Something we do not have a category for in our current astronomical taxonomy? The scientific consensus remains firmly in favour of the natural explanation. Charge exchange X-rays are exactly what we should expect from a comet. The intensities and spectral features appear consistent with known physics. There is no X-ray anomaly that demands an exotic interpretation. But the very fact that we can now observe 3I-ATLAS in this new wavelength opens possibilities that were previously inaccessible. If there was something unusual about the object's core structure, something that affected how gases are produced and released, we might see hints of it in the X-ray data as analysis continues. What strikes me most about the X-ray observations is not any single measurement, but the broader picture they represent. For the first time in human history, we're studying an interstellar object across the entire electromagnetic spectrum. Visible light shows us the dust and the coma. Infrared reveals the molecular composition. Ultraviolet tracks the ionization of gases. Radio waves probe the large-scale structure. And now X-rays illuminate the violent boundary where our solar system's wind meets material from another star. Each wavelength is a different window into the same object. And through these windows we're assembling the most complete portrait ever created of a visitor from beyond. The X-ray story does not end with XMM Newton and X-RISM. As 3I-ATLAS approaches its closest point to Earth on December 19th, more observations are planned. The X-ray telescopes will continue their vigil gathering data that will take months to fully analyse. And in the background, a question lingers. What else might we see if we look hard enough? What other invisible light might be streaming from this ancient traveller? Are there wavelengths we have not yet checked? Signals we have not yet searched for? This brings us to one of the more controversial aspects of the 3I-ATLAS story. Avi Loeb has repeatedly suggested that someone should be listening for radio signals, specifically signals near the hydrogen line at 1420 MHz. This is the frequency that the famous WOW signal was detected at in 1977. Loeb has noted a rough alignment between the sky position of 3I-ATLAS and the direction from which the WOW signal appeared to originate. He does not claim this is evidence of a connection, but he argues that the coincidence is interesting enough to warrant a targeted search. So far, neither the Allen Telescope Array nor the Green Bank Observatory has reported any unusual radio emissions from 3I-ATLAS. The silence continues, but Loeb would say that absence of evidence is not evidence of absence, and the search he advocates is ongoing. What we know for certain is this: 3I-ATLAS is emitting X-rays. Those X-rays are produced through charge exchange interactions that we understand well. The extended halo of X-ray emission confirms that the comet is actively releasing gas into its environment, and the spectral signatures suggest a composition that includes carbon, nitrogen, and oxygen-bearing molecules. All of this is consistent with a natural interstellar comet. None of this proves that interpretation beyond all doubt. The invisible light has spoken, but its message is incomplete. And as we turn our attention to what the visible light has revealed, a new puzzle emerges. 3I-ATLAS has been changing, not just in brightness, not just in activity, it has been changing colour. And that transformation tells a story that even the X-rays cannot fully explain. The colour that should not have changed. In late August 2025, the Gemini South Telescope in Chile captured one of the first detailed colour images of 3I-ATLAS. The comet appeared distinctly red. Not the warm red of a sunset or the deep red of a rose. This was the cold red of iron oxide, the red of ancient rust on a cosmic scale. Astronomers noted this colour with interest but not alarm. Many objects in the outer solar system appear reddish due to organic compounds on their surfaces, compounds that have been processed by billions of years of cosmic ray bombardment. The red colour of 3I-ATLAS seemed consistent with an object that had spent eons drifting through the radiation bath of interstellar space. Then something changed. On November 26, 2025, exactly 3 months after those first colour observations, the Gemini North Telescope in Hawaii turned its multi-object spectrograph toward the interstellar visitor. The comet had passed its closest approach to the Sun nearly a month earlier. It was now moving away. cooling down. Theoretically, it should have been returning to a quiescent state. The intense activity triggered by perihelion should have been subsiding, and in visible images that seemed to be happening, the coma remained relatively compact. The tail was modest, but the colour was wrong. 3I-ATLAS was no longer red. It had turned green. Not a subtle shift in hue. A dramatic transformation visible in the processed images that combined exposures through blue, green, orange, and red filters. The coma now displayed a distinctive greenish glow, a colour that told astronomers something fundamental about the comet's chemistry had changed. The green colour of comets is one of the more visually striking phenomena in our solar system. When you see photographs of famous comets like Lovejoy or Wirtanen or the recent Pons Brooks, often called the Mother of Dragons comet, you may notice that ethereal green tints surrounding their nuclei. This colour comes from a molecule called diatomic carbon. Two carbon atoms bonded together designated C2 in scientific notation. When sunlight strikes these molecules, they absorb energy and then re-emit it as visible light. That emission happens to fall in the green part of the spectrum. It is essentially a cosmic fluorescence, the comet glowing in a colour determined by quantum mechanics and molecular structure. The presence of C2 in a comet is not unusual. It is detected in many solar system comets, particularly when they become active near the Sun. The interesting thing about 3I-ATLAS is not that it contains diatomic carbon, but when that carbon became visible. In August, the comet appeared red. The green signature was absent, or at least too faint to dominate the colour balance. By November, the green had taken over. Something had happened in the intervening months to release or produce the molecules responsible for this dramatic colour shift. The most straightforward explanation involves the comet's passage through perihelion. When 3I-ATLAS swung closest to the Sun, on October 29th, it experienced the most intense heating of its journey through our solar system. Solar radiation penetrated deeper into its surface than ever before. Pockets of ice that had remained frozen for billions of years began to sublimate. New materials were exposed, new chemical reactions became possible, and among the gases released were the precursors to diatomic carbon. C2 does not typically come directly from the nucleus. It is what chemists call a daughter species, a secondary product created when parent molecules break apart under solar radiation. The most common parent is thought to be C3, tricarbon. When ultraviolet light from the Sun strikes C3 molecules in the coma, they fragment producing C2. Other organic molecules can also serve as sources. The details depend on the specific chemistry of the comet, which varies from object to object. What this means is that the green glow we now see in 3I-ATLAS is evidence of ongoing chemical evolution. The comet is not static. It is transforming as we watch. The solar stress test of perihelion triggered changes that are still unfolding weeks later. Heat takes time to penetrate icy bodies. Materials released at the surface can take days or weeks to disperse through the coma and undergo photodissociation. The green colour we observe today may be the delayed signature of processes that began during the comet's closest approach to the Sun. This is fascinating from a scientific perspective because it gives us a window into the interior composition of 3I-ATLAS. The red colour seen in August likely represented surface materials, the outermost layers that had been exposed to interstellar radiation for billions of years. These layers were transformed by cosmic rays into dark, reddish organic compounds. The technical term is tholins, complex carbon-nitrogen polymers that form when simple molecules are irradiated in the absence of oxygen. Tholins are found throughout the outer solar system, on Titan, on Pluto, on countless small icy bodies in the Kuiper belt. The red colour of 3I-ATLAS was consistent with an ancient surface, processed by its long journey through interstellar space. But as the Sun heated the comet, that ancient surface began to erode. Fresh materials from deeper within the nucleus were exposed for the first time in eons. These materials had been shielded from radiation. They retained more of their original chemistry, and among that original chemistry were the carbon-bearing compounds that now produce the green glow. In a sense, we're watching 3I-ATLAS shed its interstellar skin. The red coating it acquired during its journey is being stripped away, revealing the greener, fresher material beneath. The team at Neue Lab, which operates the Gemini telescopes, noted this colour evolution in their December release. They emphasize that many solar system comets display similar green hues when activated by the Sun. The mechanism is well understood. The physics is conventional. There is nothing in the color change that demands an exotic explanation. 3I-ATLAS is behaving like a comet because it is a comet. But here is where I want you to think carefully about what we are observing. The color shift from red to green tells us that 3I-ATLAS has a layered structure, an outer shell of radiation-processed material surrounding an inner core of more pristine ices. This structure developed over an immense timescale. The outer layer accumulated damage atom by atom as cosmic rays struck the surface during the comet's journey through interstellar space. That journey lasted billions of years. Billions of years of isolation in the coldest, darkest reaches between the stars. And now, in just a few months of solar heating, that ancient surface is being erased. Think about what this means philosophically. We are witnessing the destruction of a record. The red surface of 3I-ATLAS was a kind of cosmic diary, a chemical history of every stellar wind, every cosmic ray, every photon of starlight that struck it during its interstellar voyage. That record is billions of years old. It predates our Sun. It may predate most of the stars currently shining in our galaxy, and we are watching it burn away. There is something almost tragic about that. The very process that allows us to study 3I-ATLAS is also destroying the evidence of its past. The heat that activates the comet and makes it visible also erases the surface chemistry that could have told us most about its journey. We are reading a book whose pages catch fire the moment we turn them. Every observation we make comes at the cost of information we can never recover. Some astronomers have suggested that this is why interstellar comets like 3I-ATLAS are so valuable despite their fleeting nature. They arrive in our solar system carrying chemical fingerprints from other star systems, fingerprints that we could never obtain any other way. Even our fastest spacecraft would take tens of thousands of years to reach the nearest star. But interstellar comets come to us. They deliver samples from the cosmos directly to our doorstep. All we have to do is be ready to study them during their brief visit. The green glow of 3I-ATLAS is more than a colour. It is a message. It tells us that this object contains carbon chemistry complex enough to produce C2 when irradiated by sunlight. It tells us that the nucleus has structure with distinct layers that have experienced different histories. It tells us that the comet is actively evolving, responding to its new solar environment in real time. And it raises questions about what other chemical surprises might be waiting for us in the data still being analysed. Avi Loeb has commented on the colour change as well, though his interpretation differs from the mainstream. He notes that 3I-ATLAS has now changed colour multiple times since its discovery. First it was red. Then observation suggested it might have shifted to different hues during its approach to perihelion. Now it is green. Loeb suggests that these colour changes could theoretically be consistent with an object that has different regions or components, with different optical properties. He has speculated about the possibility of an artificial outer shell that behaves differently from a natural comet's surface. But he acknowledges that this interpretation is highly speculative, and that the conventional explanation involving natural outgassing and chemical evolution fits the data well. The scientific community broadly agrees that the colour evolution of 3I-ATLAS is exactly what we should expect from an interstellar comet experiencing its first close passage near a star after billions of years in deep space. The red to green transition mirrors what we see in some solar system comets. The timing correlates with the post-perihelion phase, when deep-seated activity continues even as the surface cools. There is nothing in the colour data that requires us to invoke anything beyond standard cometary physics. But as mentioned before, the absence of anomaly is not the same as complete understanding. We are still learning what normal means for interstellar comets. We have exactly two previous examples. Oumuamua was so small and fast that we barely glimpsed it before it was gone. Borisov was more cooperative but still limited in what it revealed. 3I-ATLAS is giving us more data than both of them combined, and that data is teaching us that these objects can be surprising in ways we did not anticipate. The colour story connects to a larger theme that runs through all of our observations of 3I-ATLAS. This object is complex, it has history, it has structure. It is not a uniform ball of ice but a differentiated body, with distinct regions and layers. The more we study it, the more details emerge, and those details are raising questions about another aspect of the comet that has genuinely puzzled researchers. Its chemistry is not just complex. In some ways, it is unprecedented. The green glow comes from carbon, but carbon is just one piece of the chemical puzzle. In the next stage of our investigation, we need to examine what else is streaming off 3I-ATLAS. What molecules are present in its coma? What ratios define its composition? And why those ratios are unlike anything we have ever measured in any comet before? The answers are strange, and they lead us into territory where the line between familiar and alien becomes uncomfortably blurred. A chemistry never seen before. When the James Webb Space Telescope turned its infrared eyes toward 3I-ATLAS in early August 2025, scientists expected to find water. Water ice is the defining feature of comets. It is what distinguishes them from asteroids. It is what produces the spectacular tales that have inspired wonder and terror throughout human history. Comets are often described as dirty snowballs, balls of ice mixed with dust and rock that sublimate as they approach the warmth of a star. Water should be the dominant volatile. Water should drive the activity. Water should be the headline finding. Instead, the James Webb found carbon dioxide. The infrared spectra revealed a coma dominated by CO2, carbon dioxide gas streaming off the nucleus in quantities that dwarf the water signature. The ratio of carbon dioxide to water was measured at 7.6 to 1. That is not a subtle deviation from normal. That is among the highest CO2 to H2O ratios ever recorded in any comet. Solar system comets typically show water as their primary volatile, with carbon dioxide playing a secondary role. 3I-ATLAS has inverted that relationship. It is a carbon dioxide comet with water as an afterthought. This finding immediately raised questions about the comet's origin. Carbon dioxide freezes at lower temperatures than water. In the coldest regions of a protoplanetary disk far from the central star CO2 ice can form more readily than water ice. If 3I-ATLAS originated in such a region around its parent star, it might naturally have incorporated more carbon dioxide than water into its structure. Alternatively, the comet's long journey through interstellar space might have altered its composition. Cosmic rays can break apart water molecules over billions of years, while carbon dioxide might be more resistant to such degradation. But the James Webb discovery was just the beginning. As observations continued through August, September and October, a more complete chemical picture emerged. And that picture grew stranger with each new data point. The Atacama Large Millimeter-Submillimeter Array, known as ALMA, sits high in the Chilean desert. At an altitude of 5,000 meters, it operates above most of the water vapor in Earth's atmosphere, giving it an exceptionally clear view of the cosmos at radio and microwave wavelengths. Between late August and October 2025, a team led by Martin Cordner at NASA's Goddard Space Flight Center used ALMA to study 3I-ATLAS. They were looking for specific molecules that emit radiation at millimeter wavelengths, molecules that could tell them more about the comet's composition and activity. What they found has challenged our understanding of cometary chemistry. ALMA detected methanol, CH3OH, a simple alcohol molecule that is common in the interstellar medium and has been found in other comets. But the amount of methanol coming from 3I-ATLAS was extraordinary. Approximately 40 kilograms of methanol were being released every second. That is not a typo. 40 kilograms per second. A continuous stream of alcohol gas pouring off the nucleus into space. To put this in perspective, methanol typically makes up about 2% of the total vapor coming off a solar system comet. In 3I-ATLAS, methanol comprises roughly 8% of the total outgassing. That is 4 times the normal fraction. The production rate places 3I-ATLAS among the most methanol-rich comets ever observed. But the methanol finding was only half of the puzzle. ALMA also detected hydrogen cyanide, HCN, a molecule consisting of 1 hydrogen, 1 carbon, and 1 nitrogen atom. Hydrogen cyanide is interesting for several reasons. It is toxic to most life forms on Earth. It is also considered a potential precursor for the formation of amino acids and nucleic acid bases. The same molecule that could kill you might have played a role in the origin of life itself. A beautiful paradox written in the language of chemistry. The hydrogen cyanide was detected emanating from near the comet's nucleus. Production rates varied between 1/4 and 1/2 kilogram per second. Smaller than the methanol output, but still significant. And when Cordina's team calculated the ratio of methanol to hydrogen cyanide production, they found something unprecedented. The ratio was among the highest ever measured in any comet. Only one other comet has shown higher values, C 2016R2, also known as Pan-STARRS. That object was so unusual that astronomers classified it as anomalous. It was rich in carbon monoxide but poor in hydrogen cyanide. Its coma glowed blue instead of green. It defied categorization within the normal taxonomy of cometary objects. 3I-ATLAS is now approaching that same level of chemical strangeness. Its methanol to HCN ratio places it at the extreme end of the cometary distribution. Not impossible, not supernatural, but rare, unusual, worth paying attention to. There is another aspect of the methanol finding that has puzzled researchers. In most comets, the volatile gases detected in the coma come directly from the nucleus. Ice sublimates from the surface or from vents and jets and streams into space. The source is the solid body at the centre. But the ALMA data suggest that methanol in 3I-ATLAS is not only coming from the nucleus, it appears to be present throughout a larger volume of the coma, as if it is being produced or released from somewhere beyond the immediate surface. One possible explanation involves distributed sources. Grains of dust ejected from the nucleus might contain pockets of methanol ice. As these grains drift away from the comet and continue to warm in sunlight, they release their trapped volatiles. The methanol appears spread through the coma because it is coming from countless tiny ice-bearing particles rather than from one central location. Another possibility involves chemical reactions within the coma itself. Parent molecules released from the nucleus might break apart or combine under solar radiation to produce methanol as a secondary product. This would be unusual since methanol is typically considered a parent, species that survives largely intact from the nucleus. But unusual does not mean impossible, and 3I-ATLAS has already shown us that it does not always follow the standard playbook. A third possibility, more speculative but worth mentioning, involves the internal structure of the nucleus itself. If 3I-ATLAS is not a uniform body, but rather an aggregate of distinct components, then different regions might have different compositions. The methanol-rich areas might be distributed in a patchy or heterogeneous fashion throughout the comet. As the nucleus rotates and different faces are exposed to sunlight, the outgassing pattern would shift. The coma would reflect this complexity, with methanol appearing in unexpected locations. The research team emphasized that the nucleus of 3I-ATLAS is likely heterogeneous rather than uniform. This is actually consistent with what we know about solar system comets. Objects like 67P Churyumov-Gerasimenko, which was studied in detail by the Rosetta mission, have shown complex internal structures, different lobes, layered deposits, variations in composition from place to place. There is no reason to expect an interstellar comet to be any simpler. What makes the chemistry of 3I-ATLAS particularly intriguing is the combination of all these findings: high carbon dioxide, high methanol, unusual methanol to HCN ratio, possible distributed methanol sources. Each individual observation could be explained within the framework of conventional cometary science, but together they paint a picture of an object that sits at the edge of the known population, an outlier, a boundary case that tests the limits of our models. Avi Loeb has noted that the chemical composition of 3I-ATLAS bears some resemblance to industrial processes on Earth. He points out that nickel was detected in the comet's coma without corresponding iron. This ratio mirrors that of nickel-based alloys used in aerospace engineering. He suggests that the unusual chemistry could theoretically be consistent with manufactured materials, but he also acknowledges that natural processes can produce similar signatures, and that we do not have enough data to draw firm conclusions. The mainstream scientific response to these chemical findings has been measured. Yes, 3I-ATLAS is unusual. Yes, its composition differs from typical solar system comets, but it came from another star system. We should expect some differences. The question is whether those differences fall within the range of natural variation, or whether they point to something fundamentally distinct. Consider an analogy. Imagine you're a zoologist who has spent your entire career studying birds in North America. You know every species, every plumage pattern, every song and behaviour. Then one day someone brings you a bird from Australia. It looks different, it acts different, its songs are unfamiliar. You might be tempted to say this is not a real bird, but of course, it is a bird. It is just a bird shaped by different evolutionary pressures in a different environment. Its strangeness reflects its origin, not its fundamental nature. 3I-ATLAS may be the cosmic equivalent of that Australian bird. Its chemistry is strange to us because it formed under conditions we have never directly observed. Around a star whose properties we do not know, in a protoplanetary disk whose temperature profile and composition were different from ours. Every atom in 3I-ATLAS carries information about that alien environment, information encoded in ratios and abundances that seem wrong only because our frame of reference is so limited. The methanol and hydrogen cyanide findings have another implication that extends beyond pure chemistry. Both of these molecules are considered relevant to astrobiology. Methanol can participate in reactions that produce more complex organic compounds. Hydrogen cyanide can combine with water and ammonia to form amino acids under the right conditions. The detection of these molecules in high abundance suggests that 3I-ATLAS carries the raw materials from which life could theoretically arise. This connects to a hypothesis called panspermia, the idea that life or its precursors might be distributed throughout the cosmos by comets and asteroids. If interstellar objects like 3I-ATLAS routinely carry organic molecules, then they might seed planetary systems with the building blocks of biology. Life on Earth might have received a boost from similar visitors billions of years ago. We might be the distant descendants of chemistry that began around another star. Loeb has described 3I-ATLAS as a potential friendly interstellar gardener, an object that distributes the seeds of life as it wanders from star system to star system. He contrasts this with the possibility that such objects could also distribute harmful materials. Hydrogen cyanide, after all, is a potent toxin. The same molecule that might help create life could also destroy it under different circumstances. The chemistry is neutral. Only context determines whether it leads to creation or destruction. As we continue to study the molecular composition of 3I-ATLAS, more surprises may emerge. The data pipeline is still flowing. Observations made in October and November are still being processed. Papers are being written. Analyses are being refined. The picture we have today is more complete than it was a month ago, but less complete than it will be a month from now. What we know for certain is that 3I-ATLAS is chemically rich. It carries an inventory of molecules that tell a story of formation preservation and now transformation as it encounters our Sun. That story is written in methanol and hydrogen cyanide, in carbon dioxide and water, in nickel vapor and diatomic carbon. And as we learn to read that story, we are learning something about the diversity of chemistry across the galaxy, about the range of conditions under which comets can form, about the ingredients that drift between the stars waiting to fall into new solar systems and perhaps new worlds. The methanol keeps flowing, 40 kilograms every second, a river of alcohol streaming from an ancient visitor. And the question remains, what else is 3I-ATLAS hiding? What other molecules wait to be discovered? And what will they tell us about the object at the center of this cosmic storm? The methanol paradox. Let me take you deeper into the methanol mystery, because there is something here that deserves more attention than it has received. When scientists say that methanol comprises 8% of the vapor coming off 3I-ATLAS, they are describing something that should make every astrochemist pause. This is not just a high number. This is a number that forces us to ask fundamental questions about how this comet formed and what it is made of. In our solar system, the chemistry of comets follows patterns that we have come to understand through decades of observation and mission data. The Rosetta spacecraft spent 2 years studying Comet 67P up close. It sniffed its gases. It tasted its dust. It watched the nucleus tumble and outgas through an entire orbit. From Rosetta and from ground-based observations of hundreds of other comets, we have built a picture of what solar system comets contain. Water dominates. Carbon dioxide and carbon monoxide are present in varying amounts. Methanol appears, but typically as a minor component. 2% of the vapor budget, maybe 3% in unusual cases. The chemistry is complex but bounded. There are rules. 3I-ATLAS appears to be violating those rules, or more precisely, it appears to be following different rules. Rules that applied wherever it formed around whatever star gave it birth. The 8% methanol fraction is remarkable because methanol is not an easy molecule to make in large quantities. It forms through chemical reactions on the surfaces of tiny ice grains in cold molecular clouds. Carbon monoxide molecules land on these grains and react with hydrogen atoms to build up the methanol structure one piece at a time. The process requires specific conditions, very low temperatures, the presence of hydrogen in atomic form, enough time for the reactions to proceed, too warm and the molecules evaporate before they can react, too few hydrogen atoms and the synthesis stalls. The abundance of methanol in any icy body depends on the environment in which it formed. If 3I-ATLAS carries 4 times the typical methanol fraction, then the environment in which it formed was different from the environment in which our comets formed. Perhaps the protoplanetary disk around its parent star was colder on average, allowing more methanol synthesis to occur. Perhaps that disk contained different proportions of carbon and hydrogen favouring methanol production. Perhaps the comet spent time in a region of the disk where conditions were just right for methanol to accumulate. We do not know the answer, but the methanol abundance is a clue, a fingerprint of an alien stellar nursery. There is another aspect of the methanol finding that has received less attention, but may be equally significant. The ALMA observations suggested that methanol is present not just near the nucleus, but distributed throughout a larger volume of the coma. As mentioned before, this could indicate that methanol is coming from icy grains in addition to or instead of directly from the surface. But there is a more provocative interpretation. Some researchers have speculated that methanol might be forming within the coma itself, not just sublimating from existing ice, but actually being synthesized in situ through chemical reactions in the gas phase. This would be unusual. Methanol is generally considered a parent species that comes intact from the nucleus, but unusual does not mean impossible, and 3I-ATLAS is proving to be an unusual object. The conditions in a cometary coma are extreme by terrestrial standards, but also different from the interstellar medium. There is radiation from the sun driving photochemistry. There is dust providing surfaces for reactions. There are multiple gas species mixing and colliding. In principle, complex chemistry could occur. New molecules could form that were not present in the original ice. The coma would become a kind of cosmic laboratory, synthesizing compounds in real time. If methanol is being produced in the coma of 3I-ATLAS, then its chemistry is even more interesting than a simple high abundance would suggest. It would mean the comet is not just releasing its stored inventory, but actively creating new materials as it travels through our solar system. The object would be chemically dynamic in a way we have not observed before. I want to be careful here because this is speculative. The evidence for distributed methanol production is suggestive but not conclusive. The simpler explanation remains that methanol-rich grains are releasing their contents as they warm in sunlight. This explains the observations without requiring any exotic chemistry, but the possibility of in situ production is intriguing enough that researchers are actively investigating it. The methanol findings connect to a larger question about the relationship between interstellar chemistry and planetary chemistry. Methanol is abundant in the clouds of gas and dust where stars form. It has been detected in countless molecular clouds throughout our galaxy. When these clouds collapse to form stars and planets, the methanol becomes incorporated into the icy bodies that eventually become comets. In a sense, comets are time capsules preserving the chemistry of stellar birth regions. If 3I-ATLAS truly is an interstellar comet, then its methanol comes from a stellar birth region we have never sampled before. The cloud in which its parent star formed might have been richer in methanol than the cloud that produced our sun. The chemistry of that cloud is now visible to us encoded in the vapour, streaming off this ancient visitor. Every molecule of methanol that ALMA detects is a messenger from another stellar nursery, a tiny piece of information about conditions that existed billions of years ago in a completely different part of the galaxy. There is something almost philosophical about this. We spend billions of dollars building spacecraft to visit other worlds. We dream of missions to other star systems that would take generations to complete. And here, floating through our solar system at no cost to us, is a sample from another star. A fragment of alien chemistry delivered directly to our doorstep. All we have to do is point our telescopes and read the message. The methanol paradox has implications for our understanding of chemical diversity across the cosmos. If different stellar environments produce comets with different chemical compositions, then the range of possible cometary chemistry is much broader than our solar system alone would suggest. Some interstellar comets might be water-dominated like our local population. Others might be carbon dioxide-dominated like 3I-ATLAS. Still others might contain molecules we have never detected in any comet. The possibilities multiply as we consider the billions of stars that have formed and died since the universe began. This brings us to an uncomfortable question. How much can we generalize from our solar system? For most of astronomical history, we had exactly one example of a planetary system, our own. We assumed that other systems would be similar because we had nothing else to go on. Then exoplanet discoveries showed us that our assumptions were wrong. Hot Jupiters, super-Earths, planets orbiting binary stars. The diversity of planetary architectures far exceeded our imagination. Could the same be true for cometary chemistry? Are we about to discover that the comets of other star systems are wildly different from our own? 3I-ATLAS hints at this possibility. Its methanol abundance is not just a data point. It is a challenge to our models, a reminder that the universe is under no obligation to match our expectations. The panspermia hypothesis gains new texture in light of these findings. If interstellar objects carry diverse chemical payloads, then different planetary systems might receive different packages of prebiotic materials. A world seeded by a methanol-rich comet might develop different organic chemistry than a world seeded by a water-dominated comet. The pathways to life might branch early depending on the random deliveries from passing interstellar objects. In a sense, life in different parts of the galaxy might have different chemical ancestors, different primordial soups from which complexity emerged. Avi Loeb has pushed this idea further, suggesting that if interstellar objects can carry organic precursors, they might also carry more complex biological materials, dormant microbes, frozen spores, the seeds of life in a more literal sense. He points to 3I-ATLAS as evidence that such delivery mechanisms exist. Whether they carry inert chemistry or active biology remains an open question. But the methanol streaming off 3I-ATLAS proves that complex organic molecules can survive the journey between stars. Whatever was frozen into this object billions of years ago is now being released into our solar neighborhood. The paradox of methanol extends beyond its abundance to its implications. Here is a molecule that could nurture life or destroy it depending on the context. Methanol is toxic to humans. It causes blindness and death if ingested. But in the right chemical environment under the right conditions, it can participate in reactions that build amino acids and other biological molecules. It is both poison and potential medicine, a dual nature written into its molecular structure. 3I-ATLAS releases 40 kilograms of this ambiguous substance every second, spraying it into the void as it rushes past our planet. The methanol will disperse through the inner solar system, mixing with the solar wind and the cosmic background. Some of it will eventually fall into the gravity wells of planets. Perhaps a few molecules will drift into Earth's upper atmosphere. Visitors from another star settling gently onto a world they know nothing about. The chemistry continues to evolve as 3I-ATLAS moves away from the Sun. The outgassing rates will change. The molecular ratios may shift. New species may appear or disappear as conditions change. Every observation captures a snapshot of a dynamic system. A comet in transformation responding to an environment completely unlike anything it experienced during its billion-year journey through interstellar space. We are watching chemistry happen in real time. Reactions that have been frozen since before the solar system existed are now proceeding as ancient ice meets solar radiation for the first time. The methanol paradox is not just about abundance. It is about witnessing a process that connects the birth of stars to the possibility of life. About understanding that comets are not dead rocks, but active participants in the cosmic circulation of matter. About recognizing that an object from another star carries within it the potential to change our understanding of where we came from and whether we are alone. The 40 kilograms per second keep flowing, a stream of organic possibility from an impossible distance. And as we turn to examine what our space telescopes have revealed in their latest images of 3I-ATLAS, we will discover that the chemical surprises are matched by visual surprises equally profound. Something in those images does not look quite right, and explaining what we see requires us to consider possibilities that push against the boundaries of conventional understanding. What Hubble saw that no one expected. The Hubble Space Telescope has been watching 3I-ATLAS since shortly after its discovery. On July 21, 2025, Hubble captured its first image of the interstellar visitor using its Wide Field Camera 3. At that time, the comet was still approaching the Sun on the inbound leg of its journey. The image showed a fuzzy teardrop shape, a coma of gas and dust surrounding the invisible nucleus at the center. Background stars appeared as streaks because Hubble was tracking the moving comet rather than the fixed stellar background. Everything looked more or less as expected. Another comet caught in the act of outgassing. Nothing alarming. But there was something unusual about that first image, something that astronomers noted but initially dismissed as a geometric artifact. The teardrop shape of the coma was oriented toward the Sun rather than away from it. Let me explain why this matters. When a typical comet approaches a star, the solar wind and radiation pressure push material away from the Sun. Dust and gas released from the nucleus stream outward, forming the characteristic cometary tail. That tail always points away from the Sun regardless of which direction the comet is moving. It is one of the most reliable visual signatures of cometary behavior. The Sun pushes. The tail extends in the opposite direction. But in the July Hubble image, the brightest material around 3I-ATLAS appeared to extend toward the Sun. This sunward extension is sometimes called an anti-tail. The term is slightly misleading because it is not really a tail in the usual sense. It is material that happens to be positioned between the comet and the Sun from our viewing angle. Anti-tails can occur for purely geometric reasons. If the comet has a broad fan of dust particles, and we happen to be viewing it, edge on some of that dust will appear to point sunward even though it is not actually moving toward the Sun. Astronomers initially assumed this was the case with 3I-ATLAS. A geometric illusion, a matter of perspective, nothing more. Then November came, and Hubble looked again. On November 30th, 2025, the Hubble Space Telescope re-observed 3I-ATLAS with the same wide-field camera 3 instrument. A month had passed since perihelion. The comet was now on the outbound leg of its trajectory, moving away from the Sun and toward its eventual encounter with Jupiter. The viewing geometry had changed. The Sun-Comet-Earth angle was different. If the anti-tail in the July image had been purely geometric, it should have disappeared or shifted dramatically. It did not. The November image shows the same teardrop shape with the same sunward extension. The coma still appears oriented toward the Sun. The anti-tail persists, and now the geometric explanation becomes harder to sustain. The viewing angle has changed, but the morphology has not. Something about the comet itself is producing this sunward asymmetry. Avi Loeb was quick to comment on the new Hubble image. In a blog post published shortly after the data became available, he offered an interpretation that goes beyond conventional cometary physics. He suggested that the sunward teardrop might be associated with a swarm of macroscopic non-volatile objects that separated from 3I-ATLAS during its perihelion passage. Let me unpack what this means. When 3I-ATLAS swung closest to the Sun, it experienced significant heating. That heating produced the non-gravitational acceleration that NASA's navigators have measured. Material was ejected from the nucleus. The comet pushed back against that ejection. This is normal cometary behavior. But Loeb suggests that among the material ejected might have been solid objects. Not just gas and dust, but chunks of rock or ice or something else. Objects large enough that radiation pressure does not push them away. Objects that would continue to drift in the comet's original direction, maintaining a position closer to the Sun than the main nucleus. If this interpretation is correct, then the sunward extension in the Hubble images is not a tail at all. It is a debris field, a collection of fragments trailing behind the comet in its orbit. Not behind in the sense of the tail which points away from the Sun, behind in the sense of orbital motion. Closer to the Sun because they separated before the comet reached its current position. Loeb calculated that if these hypothetical objects overlapped with 3I-ATLAS at perihelion, they would now be roughly 60,000 kilometers sunward of the main nucleus. This matches the scale of the anti-tail seen in the November image. The agreement is striking, perhaps coincidental, perhaps meaningful. The data alone cannot tell us which. The mainstream astronomical community has responded cautiously to this interpretation. Anti-tails are known phenomena with well-understood optical causes. The persistence of the feature across multiple viewing geometries is unusual, but not unprecedented. Complex dust distributions can produce persistent asymmetries. The debris field hypothesis is interesting, but not required to explain the observations. Still, the Hubble images have added fuel to the ongoing debate about the nature of 3I-ATLAS. If the sunward feature is composed of solid fragments rather than gas and dust, then the comet is fragmenting, losing pieces of itself as it passes through our solar system. This would be significant regardless of whether the fragments are natural or artificial. It would mean that 3I-ATLAS is not surviving its solar encounter intact. It is shedding material that will remain in our solar system long after the main body has departed. The European Space Agency's JUICE spacecraft has provided additional imagery that complicates the picture further. On November 2nd, 2025, JUICE was en route to Jupiter when it turned 5 of its scientific instruments toward 3I-ATLAS. The spacecraft was about 41 million miles from the comet at the time. Most of the data will not reach Earth until February because JUICE is using its main antenna as a heat shield during its passage close to the Sun. But the mission team could not wait that long. They downloaded a quarter of a single image from the spacecraft's navigation camera. Just a fragment of a fragment, a teaser of what is to come. And even in that low-resolution partial frame, 3I-ATLAS revealed surprises. The image shows a bright nucleus surrounded by a glowing coma. So far, so normal. But extending from the coma are 2 distinct tails. One stretches upward in the image orientation. This is the plasma tail, a stream of ionized gas being pushed directly away from the Sun by the solar wind. The other tail is fainter and extends in a different direction. This is the dust tail, a stream of solid particles following their own orbital paths influenced by both solar gravity and radiation pressure. The presence of 2 tails is actually expected for active comets. What surprised the ESA team was the level of activity so soon after perihelion. 3I-ATLAS appeared more vigorous than models predicted. It was outgassing more aggressively, shedding more material. The comet was described as showing signs of activity that scientists found surprising given the timing. Remember the quiet post-perihelion observations from early November. The compact coma without a clear tail, the apparent lack of dramatic activity. Those observations came from ground-based telescopes with less resolution than JUICE. Now the spacecraft images suggest that something was happening after all, activity that was hidden from our view, or too subtle for ground-based instruments to detect. 3I-ATLAS was not dormant. It was active. Perhaps more active than we realized. This discrepancy between ground-based and space-based observations highlights a fundamental challenge in studying distant objects. We can only see what our instruments allow us to see. 3I-ATLAS has been observed in visible light, infrared, ultraviolet X-rays and radio waves. Each wavelength reveals different features. Each instrument has different sensitivity. The picture we assemble is necessarily incomplete. Fragments of truth that we try to stitch into a coherent narrative. The Hubble and JUICE images add new fragments, a persistent anti-tail, dual-tail structures, unexpected levels of post-perihelion activity. Each observation is consistent with natural cometary behavior. None requires an exotic explanation, but together they paint a portrait of an object that does not quite fit our templates. An outlier in visual morphology, just as it is an outlier in chemical composition. Loeb has compiled what he calls a list of anomalies, visual features and behaviors that distinguish 3I-ATLAS from typical solar system comets. The anti-tail is one. The apparent lack of tail in some observations while showing dramatic tails in others is another. The colour changes we discussed earlier add to the list. Each individual anomaly can be explained, but the accumulation of unusual features has convinced Loeb that something deserves closer scrutiny. The scientific community remains divided on how to interpret this accumulation. Some argue that interstellar comets should be expected to show anomalies. They formed under different conditions. They have different compositions. They experience different histories. Unusual is not the same as unnatural. Others acknowledge that the case for 3I-ATLAS being a completely natural object is strong, but not airtight. There is room for alternative hypotheses, even if those hypotheses are unlikely. What strikes me most about the imaging data is not any single frame, but the evolution we have witnessed. From July to November, 3I-ATLAS has changed. Its brightness has shifted. Its colour has transformed. Its tail structure has varied. Its activity level has fluctuated. This is a dynamic object in a dynamic environment, a comet responding to solar radiation in real time. Every image captures a moment in an ongoing story, a story that will continue to unfold as the comet approaches Earth and then recedes toward Jupiter. The images also remind us of scale. 3I-ATLAS is small by cosmic standards. Its nucleus may be as tiny as 400 meters across, perhaps as large as 5 kilometers. Either way, it is a mote of matter in the vastness of space, and yet this mote has travelled farther than any human-made object. It has drifted for billions of years through conditions we can barely imagine. And now it is here, captured in pixels by telescopes named after astronomers who never dreamed such observations would be possible. December 19th will bring our clearest opportunity yet to image 3I-ATLAS. The closest approach combined with the dark skies of the new moon will allow ground-based and space-based telescopes alike to gather their highest resolution data. What will those images reveal? More surprises? More anomalies? Or the final confirmation that we are looking at nothing more than an unusually interesting natural comet? The pixels do not lie, but they also do not speak for themselves. Interpretation is required, context is essential, and as we move from what we have seen to what it might mean, we enter territory where scientific caution must compete with human curiosity. The next piece of the puzzle concerns not what 3I-ATLAS looks like, but where it is going, and the precision of its trajectory has become perhaps the most controversial aspect of this entire investigation. The 1 in 26,000 coincidence. On March 16th, 2026, 3I-ATLAS will pass by Jupiter. This is not unusual in itself. Many objects swing by the giant planet as they traverse the solar system. Jupiter's immense gravity influences everything that comes near it. But the specific distance at which 3I-ATLAS will approach Jupiter has become the subject of intense speculation. And the math behind that speculation is either remarkable or meaningless, depending on whom you ask. Every massive body in the solar system has what astronomers call a Hill sphere. This is the region of space within which that body's gravity dominates over the gravitational pull of the Sun. Inside the Hill sphere, objects can orbit the planet. Outside the Hill sphere, the Sun's gravity takes over, and objects follow heliocentric paths. The boundary between these regimes is the Hill radius. It marks the edge of a planet's gravitational territory. For Jupiter, the Hill radius depends on the planet's distance from the Sun, which varies slightly as Jupiter orbits. On March 16th, 2026, the date of 3I-ATLAS's closest approach to Jupiter, the planet will be approximately 784 million kilometers from the Sun. Plugging this value into the standard formula yields a Hill radius of 53.502 million kilometers. This is the invisible boundary surrounding Jupiter, within which captured satellites can exist. Now here is where the story becomes interesting. NASA's Jet Propulsion Laboratory maintains a system called Horizons that tracks and predicts the positions of celestial objects. Using data from over 230 observatories that have observed 3I-ATLAS since its discovery, Horizons can calculate the comet's trajectory with remarkable precision. This calculation includes the non-gravitational acceleration measured during perihelion, the outgassing push that altered the comet's path. According to the latest Horizons predictions, 3I-ATLAS will approach Jupiter to a minimum distance of 53.445 million kilometers. Compare that to the Hill radius of 53.502 million kilometers. The difference is less than 60,000 kilometers, less than 0.1%. 3I-ATLAS will skim the very edge of Jupiter's gravitational sphere of influence with a precision that borders on unbelievable. Avi Loeb has done the probability calculation. If you imagine the band of space through which 3I-ATLAS travels on its outbound journey, that band sweeps past Jupiter at various distances. The comet could pass anywhere within a range defined by observational uncertainties. The probability that a random trajectory would happen to graze Jupiter's Hill radius is approximately 1 in 26,000. Think about that for a moment. 1 in 26,000. If you rolled a 26,000-sided die, you would need to roll a specific number to match this trajectory. Not impossible, but not something that happens by accident very often. Loeb has proposed a hypothesis that explains this precision. He suggests that the non-gravitational acceleration observed during perihelion was not random outgassing, but rather a controlled course correction. A small push, designed to adjust the trajectory just enough to bring 3I-ATLAS to the edge of Jupiter's Hill sphere. In his scenario, the comet is not a comet at all, but a technological artifact. A mothership perhaps sent to seed the outer solar system with something. Let me be clear about what Loeb is claiming and what he is not claiming. He is not asserting that 3I-ATLAS is definitely artificial. He estimates the probability at 30 to 40% based on the accumulated anomalies. He's saying that the trajectory coincidence is one piece of evidence among many that warrants further investigation. He's calling for open-minded consideration of possibilities that most astronomers dismiss out of hand. The mainstream response has been skeptical, bordering on dismissive. Planetary scientists point out that the 1 in 26,000 calculation assumes a null hypothesis that may not be appropriate. The trajectory of 3I-ATLAS was not randomly selected from all possible trajectories. It was selected by the laws of physics operating on an object that originated in interstellar space. The prior probability is not uniform across all possibilities. Certain trajectories are more likely than others. Moreover, the non-gravitational acceleration has a natural explanation: comets outgas. That outgassing produces thrust. The magnitude and direction of the thrust depend on the comet's rotation, composition, and solar illumination. There is nothing about the measured acceleration that requires artificial intervention. It is exactly what you would expect from a comet-venting material near perihelion. The Hill radius coincidence itself can be understood in terms of orbital mechanics. 3I-ATLAS is on a trajectory that brings it relatively close to Jupiter. Any object on such a trajectory will pass within some distance of the Hill radius. The specific value depends on initial conditions and perturbations during the solar encounter. The coincidence Loeb highlights is striking but not necessarily meaningful. If the comet had passed at 50 million kilometers or 60 million kilometers, would that have been any less interesting? The Hill radius is a mathematically defined boundary, but nature does not know it exists. This is a crucial point. The Hill radius is a human construct, a convenient way to describe gravitational dynamics. Jupiter does not have a physical wall at 53 million kilometers. The transition from Jupiter-dominated dynamics to Sun-dominated dynamics is gradual, not sharp. An object passing just inside the Hill radius versus just outside experiences only slightly different gravitational influences. The boundary is important for classification, but neutral with respect to physics. So why does Loeb find the coincidence significant? In his view, the Hill radius represents an optimal location for certain operations. If you wanted to deploy satellites that would orbit Jupiter, you would need to deposit them inside the Hill sphere. If you wanted those satellites to be stable with minimal fuel requirements, you might position them near the Lagrange points which lie along the Hill radius. An alien spacecraft conducting reconnaissance or resource extraction might target exactly this boundary. Loeb takes the speculation further. He imagines a scenario in which 3I-ATLAS releases technological devices as it passes Jupiter. These devices would need to fire their engines to cancel out the comet's high velocity relative to Jupiter. At 65 kilometers per second relative speed, this is no trivial maneuver. But for an advanced civilization with propulsion technology far beyond our own, it might be routine. He then suggests that we should watch for new satellites appearing in Jupiter's vicinity after March 2026, objects that we did not place there. If the Juno spacecraft or future Jupiter missions detect artificial satellites around the gas giant, we would have evidence that Loeb's hypothesis is correct. Of course, we would also have evidence of something far more profound: the presence of extraterrestrial technology operating in our solar system. The scenario reads like science fiction, and to most scientists that is exactly what it is. Fiction dressed in the language of probability and orbital mechanics. The odds of 3I-ATLAS being a mothership are not 30 to 40%, but vanishingly small. The accumulated anomalies are not evidence of alien activity, but normal variation in a poorly understood category of objects. We have seen exactly 2 interstellar visitors before. Our sample size is too small to define normal. I find myself torn between these perspectives. On one hand, Loeb is a distinguished scientist who has made significant contributions to astrophysics. His willingness to consider unconventional hypotheses is admirable in a field that can be conservative to a fault. On the other hand, the history of science is littered with examples of brilliant people convincing themselves of things that turned out not to be true. Extraordinary claims require extraordinary evidence, and the evidence for artificial origin remains circumstantial at best. The Hill radius coincidence is a perfect example of how the same data can support different narratives. To Loeb, it is a suspicious precision demanding explanation. To his critics, it is a meaningless fluctuation in a random process. Neither side can definitively prove their case with current data. We are left with ambiguity, uncertainty, the discomfort of not knowing. What we can say with confidence is that the trajectory of 3I-ATLAS will bring it extraordinarily close to Jupiter's gravitational boundary. Whether this is significant or trivial depends on assumptions about the object's nature. If 3I-ATLAS is a natural comet, the coincidence is curious but not alarming. If it is something else, the coincidence takes on a different character entirely. The March 2026 encounter is months away. When it happens, our telescopes will be watching. The Juno spacecraft will be in position to observe. Any changes in the comet's behavior as it passes Jupiter will be recorded. Any anomalous acceleration, any unexpected maneuvering, any sign that 3I-ATLAS is doing something a natural comet should not do. Until then, we wait. We gather data, we refine our models, we argue about probabilities and interpretations. The universe offers no easy answers. It presents evidence and leaves us to make sense of it. 3I-ATLAS is following a path written in gravity and momentum. Whether that path was designed or accidental is a question we may never answer with certainty. But the question itself is important. It forces us to confront our assumptions about what is possible, about what might be out there, about whether we are truly alone in this vast and ancient cosmos. The 1 in 26,000 coincidence may mean nothing, or it may mean everything. The distance between those possibilities is 57,000 kilometers, a cosmic hair's breadth, an abyss of uncertainty. As 3I-ATLAS approaches its closest point to Earth, we have 5 days to gather whatever evidence we can. And among the most provocative findings is one that connects the chemistry of this interstellar visitor to the deepest question of all. Where did life come from? And could an object like 3I-ATLAS have played a role in seeding worlds across the galaxy? Seeds of life or seeds of destruction? The molecules streaming off 3I-ATLAS are not neutral. They carry implications that extend far beyond chemistry. Methanol, hydrogen cyanide, carbon dioxide, water. Each of these compounds has a story to tell about the origins of life and the possibility that we are not alone in the universe. But that story has 2 possible endings: creation or destruction, and which ending applies may depend on circumstances we do not fully understand. Panspermia is one of the oldest hypotheses about life's origins. The word comes from Greek meaning seeds everywhere. In its modern form, the hypothesis suggests that life, or the molecular precursors of life, might be distributed throughout the cosmos by comets, asteroids, and interstellar objects. Instead of life arising independently on each planet, biology might have a common ancestor that has been spreading from world to world since the early universe. The idea is not as fringe as it might sound. We know that organic molecules are abundant in space. We have detected amino acids in meteorites that have fallen to Earth. We have found complex carbon chemistry in interstellar clouds, molecular nebulae, and the cores of dying stars. The building blocks of life are not rare. They are everywhere. The question is whether those building blocks can be assembled into something living, and whether that something can survive the journey between stars. 3I-ATLAS has reignited interest in panspermia because of what it carries. The ALMA observations revealed unprecedented levels of methanol and hydrogen cyanide. Both of these molecules are considered relevant to prebiotic chemistry. Both participate in reactions that could theoretically produce the more complex molecules from which life is made. Methanol is a simple alcohol consisting of 1 carbon, 1 oxygen, and 4 hydrogen atoms. In the presence of energy and appropriate catalysts, it can react to form formaldehyde, another key prebiotic molecule. Formaldehyde in turn can participate in the Formose reaction producing sugars, including ribose, the sugar component of RNA. This chain of reactions leading from simple molecules to the nucleic acids that encode genetic information is called the RNA world hypothesis. Methanol is near the beginning of this chain, a potential starting point for molecular evolution. Hydrogen cyanide is even more directly connected to life's chemistry. Under the right conditions, HCN can react with itself and with other molecules to form adenine. Adenine is one of the 4 nucleobases that make up DNA and RNA. It is a fundamental letter in the genetic alphabet. The discovery that hydrogen cyanide can produce adenine through purely chemical processes was one of the foundational findings of prebiotic chemistry. It suggested that the building blocks of genetics might form spontaneously given the right environment. When researchers found that 3I-ATLAS produces these molecules in high abundance, the panspermia hypothesis gained new support. Here was an interstellar object delivering precisely the compounds needed to kickstart life's chemistry. If similar objects bombarded Earth during its early history, they might have provided the raw materials from which biology emerged. We might owe our existence to ancient cosmic visitors carrying the same chemistry we now observe in 3I-ATLAS. Loeb has embraced this interpretation with characteristic enthusiasm. He has described 3I-ATLAS as a friendly interstellar gardener, an object that spreads the seeds of life as it wanders from star system to star system. The methanol to hydrogen cyanide ratio, he notes, suggests an abundance of potential life-forming chemistry. 3I-ATLAS is not just passing through, it is fertilizing. But here is where the story becomes more complicated. Hydrogen cyanide is not just a precursor to life, it is also a deadly poison, one of the most toxic substances known. It kills by preventing cells from using oxygen. A small dose can cause death within minutes. Throughout human history, HCN has been used as a weapon and an agent of execution. It is the active component of Zyklon B. It is the reason cyanide appears so often in murder mysteries. The same molecule that might have helped create life can also end it with ruthless efficiency. This duality is not unique to hydrogen cyanide. Many prebiotic molecules have toxic effects. Formaldehyde is a carcinogen. Methanol causes blindness and death when ingested. The chemistry of life's origins is also the chemistry of death. The line between creation and destruction is not clear. It depends on concentration, timing, and context. Loeb has explored this darker possibility as well. He has speculated about what he calls cosmic serial killers, interstellar objects that distribute lethal chemistry as they pass through planetary systems. Instead of seeding worlds with life, these objects might sterilize them, delivering payloads of poison that wipe out emerging biospheres before they can evolve intelligence. This is a grim vision, a universe where interstellar visitors are not benevolent gardeners but indifferent exterminators, where the same processes that create life in one place destroy it in another, the universe playing dice with biology rolling creation on some worlds and destruction on others. How would we know which scenario applies to 3I-ATLAS? The answer is we would not. The molecules themselves are neutral. Methanol and hydrogen cyanide do not come with labels indicating their intended purpose. They simply exist, diffusing through the comet's coma and dispersing into interstellar space. What happens when those molecules encounter a planet depends on conditions we cannot predict or control. Consider Earth 4 billion years ago. The planet was young. Its surface was still cooling. Asteroid and comet impacts were frequent. The atmosphere was very different from today. In that environment, incoming organic molecules might have found conditions favourable for the reactions that lead to life. The toxic properties of hydrogen cyanide might have been less relevant in an ocean that contained no life to poison. The molecule could do its creative work building adenine and other nuclear bases without any victims to harm. Now consider a planet where life has already emerged, an ecosystem of organisms that use oxygen for respiration. For such a world, a bombardment of hydrogen cyanide might be catastrophic. The poison would do what poison does. Cells would suffocate. Organisms would die. The creative chemistry would be irrelevant because the destructive chemistry would act first and faster. The difference between these scenarios is not in the molecules, but in the context. 3I-ATLAS carries the same payload either way. The fate of a world receiving that payload depends on its biological state at the moment of delivery. Seeds of life for a barren planet. Seeds of destruction for an inhabited one. There is something profound about this ambiguity. It suggests that the universe does not favour life or oppose it. It simply provides ingredients. What happens with those ingredients depends on local conditions and random chance. The cosmos is not a garden designed to produce biology. It is a laboratory where experiments run constantly with outcomes that vary wildly from place to place. The 40 kilograms of methanol per second streaming from 3I-ATLAS will disperse into the solar system. Some of it may eventually find its way to planetary surfaces. Mars, the moons of Jupiter. Perhaps even Earth, though the quantities reaching us will be vanishingly small. This delivery of organic material has probably been happening throughout solar system history. Interstellar objects passing through, comets venting their payloads, dust grains drifting in the solar wind, a constant slow rain of chemistry falling on every world. Earth may have been seeded by this process. The origins of life on our planet remain mysterious despite decades of research. We do not know exactly how chemistry became biology. We do not know where the first self-replicating molecules formed, but we know that the raw materials were available: amino acids in meteorites, organic molecules in cometary impacts, the components of life delivered from space and mixed with whatever formed locally. 3I-ATLAS adds a new dimension to this picture. It shows that the chemical diversity of interstellar space may be greater than we assumed. A comet from another star system carries different proportions of molecules than our local comets. If many such visitors have passed through the solar system over billions of years, they might have contributed chemical variations that influenced the course of prebiotic evolution. The specific mixture of compounds available on early Earth might have depended partly on which interstellar objects happened to arrive at which times. This is speculation, of course. We cannot test whether 3I-ATLAS or objects like it actually contributed to life's origins on Earth. The evidence is too diffuse, the timescales too vast. But the hypothesis is consistent with what we observe. The chemistry is there. The delivery mechanism exists. The possibility is real, even if unproven. What makes 3I-ATLAS special is not that it carries organic molecules. Many comets do. What makes it special is that we can study it in detail. We can measure the production rates of methanol and hydrogen cyanide. We can watch the chemistry evolve as the comet responds to solar heating. We can compare its composition to solar system comets and identify differences that point to its alien origin. In doing so, we learn something about the range of chemical possibilities in the universe, about the variety of payloads that interstellar objects might carry to unsuspecting worlds. The seeds are flying: 40 kilograms of methanol per second, half a kilogram of hydrogen cyanide per second, carbon dioxide and water and countless other molecules joining the cosmic mix. Whether these seeds grow into life or poison existing life is not a question 3I-ATLAS can answer. The comet simply delivers. The universe simply provides. The rest is up to chance and chemistry, and the countless local conditions that determine whether a molecule becomes a building block or a weapon. As we approach the climactic days of 3I-ATLAS's closest encounter with Earth, the scientific community is mobilizing. Hundreds of observatories are coordinating their efforts. Space telescopes are adjusting their schedules. Researchers are preparing for the flood of data that December 19th will bring. And among them are a few who refuse to accept that the conventional explanation is the only explanation. Scientists who believe that keeping an open mind is not weakness but wisdom. The scientists who refuse to look away. In the months since 3I-ATLAS was discovered, a battle has been fought in the margins of scientific discourse. Not a battle over data. The data is what it is, but a battle over interpretation, over what questions are legitimate to ask, over whether certain hypotheses should be entertained at all or dismissed before consideration. On one side stands the astronomical establishment, planetary scientists with decades of experience studying comets, asteroids, and the debris of the solar system. They have seen unusual objects before. They have explained anomalies that initially seemed baffling. They know that nature is creative in ways that human imagination often fails to anticipate. For them, 3I-ATLAS is interesting but not extraordinary. An interstellar comet with unusual chemistry, a valuable scientific target, but fundamentally a natural object doing natural things. On the other side stands Avi Loeb and a small group of researchers who believe that the search for extraterrestrial technology should be taken seriously. They argue that dismissing the technological hypothesis without examination is not scientific skepticism, but scientific prejudice. They point to the accumulated anomalies of 3I-ATLAS as evidence that something deserves a closer look. They do not claim certainty. They claim that certainty in either direction is premature. This debate is not new. It has been simmering since Oumuamua passed through the solar system in 2017. That first interstellar visitor displayed strange properties that some attributed to alien technology. Its unusual shape, its lack of a visible coma, its apparent acceleration as it departed the solar system. Loeb argued that it might have been a solar sail, a piece of technology designed to ride the pressure of starlight. Most astronomers disagreed. They propose natural explanations involving unusual compositions or exotic physical processes. 3I-ATLAS has reopened this debate with fresh ammunition on both sides. Unlike Oumuamua, it clearly has a coma. It clearly outgasses. It behaves like a comet in many respects. This supports the natural interpretation. But its chemistry is extreme. Its trajectory is suspiciously precise. Its behaviour has included features that do not quite fit the standard models. This keeps the technological interpretation alive, at least in the minds of those willing to consider it. Jason Wright, an astronomer at Penn State University, has emerged as one of the most articulate critics of Loeb's approach. In a series of blog posts, Wright has systematically addressed each of the anomalies that Loeb has catalogued, the unusual chemistry. Wright argues that we should expect interstellar comets to have unusual chemistry, since they formed under different conditions. The trajectory near Jupiter's Hill radius. Wright points out that the 1 in 26,000 probability calculation rests on assumptions that may not be valid. The persistent anti-tail. Wright explains that complex dust distributions can produce such features through ordinary optical geometry. For each anomaly Loeb cites, Wright offers a natural explanation. Not proof that the natural explanation is correct, but evidence that extraordinary claims are not required. The accumulation of anomalies does not add up to evidence of technology if each individual anomaly can be explained without technology. It simply adds up to an unusual comet. But Loeb pushes back. He argues that Wright and others are applying a double standard. When a hypothesis fits their preconceptions, they accept modest evidence. When a hypothesis challenges their world-view, they demand extraordinary evidence. The technological interpretation is held to an impossible standard, while the natural interpretation is given every benefit of the doubt. There is truth on both sides of this argument. Science does and should require more evidence for extraordinary claims. A hypothesis that would revolutionize our understanding of the universe should meet a higher bar than a hypothesis that confirms what we already believe. This is not prejudice. It is appropriate calibration of prior probabilities. Extraordinary claims being less likely to be true should require more evidence to shift our beliefs. At the same time, there is a risk of closing our minds too completely. History records cases where scientists dismissed correct ideas because those ideas seemed too radical. Continental drift was mocked for decades before plate tectonics became accepted. The bacterial cause of ulcers was rejected by medical authorities, who could not accept that a simple infection explained a complex disease. Experts are not immune to motivated reasoning. They can be blinded by their own expertise. The question of how to balance skepticism and openness is not unique to 3I-ATLAS. It runs through all of science. But it takes on special urgency when the stakes are as high as they might be here. If 3I-ATLAS were confirmed to be artificial technology, it would be the most important discovery in human history. It would tell us that we are not alone, that intelligence has evolved elsewhere, that interstellar travel is possible. The implications would ripple through every aspect of human civilization. This is precisely why caution is warranted. The temptation to see what we want to see is enormous when the prize is so great. The history of SETI is littered with false alarms, signals that seemed artificial but turned out to be natural, objects that appeared designed but proved to be random. The will to believe can corrupt scientific judgment. We must guard against it even as we remain open to the possibility that one day the real thing will arrive. Loeb is aware of this tension. He has repeatedly stated that he assigns only a 30 to 40% probability to the technological hypothesis. Not a majority, not a certainty, just a significant possibility that he believes deserves investigation. He calls for more data, more observations, more willingness to look closely at features that might otherwise be dismissed. His critics argue that this framing is disingenuous. By publicly speculating about alien motherships, Loeb generates headlines and attention that distort public understanding of science. Ordinary people read that a Harvard professor thinks 3I-ATLAS might be alien technology. They do not read the caveats. They do not understand the probabilities. The nuance is lost in translation, and what remains is sensationalism. The University of Washington Center for an Informed Public has documented how discussions of 3I-ATLAS have spread through social media. They found that over 700,000 posts mention the comet by early December. Of these, more than 260,000 referenced at least one of the anomalies popularized in Loeb's writings. Posts about alien motherships and cosmic threats vastly outnumber sober discussions of cometary science. The viral narrative has taken on a life of its own, disconnected from the underlying evidence. This is the price of public engagement with provocative ideas. When scientists share speculative hypotheses with a general audience, those hypotheses escape the controlled environment of peer review. They mutate and amplify. They become stories that serve human psychological needs for wonder and fear. The scientist who started the conversation loses control of where it goes. Loeb would argue that this is not his fault. He is engaging honestly with the public about what he sees as legitimate scientific questions. If others distort his message, that is their responsibility, not his. Science should not hide in academic journals afraid to share its most interesting puzzles with the world. The public has a right to know what scientists are studying and debating. Transparency is more important than protecting people from ideas they might misunderstand. There is nobility in this view, even if it is naive about how information spreads in the modern media environment. Loeb genuinely believes that the search for extraterrestrial intelligence should be a mainstream scientific endeavour, not a fringe pursuit. He's using 3I-ATLAS to make that case. Every headline about alien motherships is also a reminder that we should be looking, that we should be building better instruments, that we should be taking the possibility of extraterrestrial technology seriously. The institutional response to Loeb has been mixed. Some colleagues admire his willingness to take risks and challenge orthodoxy. Others view him as a self-promoter who damages the credibility of the field. He has been called everything from a visionary to a charlatan. The truth is probably more complicated. He is a talented scientist with unusual ideas who has found a platform that amplifies both his insights and his errors. Meanwhile, the data continues to flow. X-ray observations, infrared spectra, radio measurements. Every telescope that can see 3I-ATLAS is contributing to the growing archive of information. Whatever conclusions emerge from this encounter will be based on that data, not on personalities or politics, not on who shouted loudest. The universe will have the final word. December 19th approaches, the climax of this observational campaign. After that, 3I-ATLAS will begin to fade. It will grow dimmer as it recedes from the sun. It will become harder to observe. By the time it reaches Jupiter in March, we may have reached the limits of what our instruments can tell us. The window is closing. The opportunity is finite. The scientists who refuse to look away are united by one thing: curiosity. Whatever their views on the nature of 3I-ATLAS, they share a drive to understand, to gather every photon of evidence, to squeeze every bit of information from the data, to answer questions that may not have answers. This is what scientists do. This is why they became scientists. An interstellar visitor does not arrive every day. When one does, you watch, you measure, you wonder. And sometimes, late at night, when the telescopes are humming and the data is streaming across continents, you allow yourself to imagine. What if? What if this is the one? What if everything is about to change? The imagination sparks and fades. The work continues. The comet keeps moving. And somewhere in the gap between what we know and what we dream lies the truth about 3I-ATLAS. March 16th, 2026. Let us project ourselves forward in time. 3 months from now. The Northern Hemisphere will be approaching spring, days will be lengthening, the chaos of the holiday season will be a distant memory, and on a date that will either be forgotten or remembered forever, 3I-ATLAS will reach its closest point to Jupiter. 3.4 million kilometers from the largest planet in our solar system, a distance so close to Jupiter's hill radius that the difference is lost in measurement uncertainty. The interstellar visitor will be moving at 65 kilometers per second relative to the gas giant. Too fast to be captured, too fast to linger, a brief encounter, and then gone forever into the darkness of interstellar space. What will happen on that day? The honest answer is we do not know. The most likely answer is nothing extraordinary. 3I-ATLAS will continue on its trajectory unperturbed by Jupiter's gravity, except for a slight deflection. It will not slow down. It will not maneuver. It will not release anything into Jovian orbit. It will simply pass by as countless natural objects have passed by Jupiter throughout the history of the solar system. But the possibility exists, however remote, that something else might happen. that the 1 in 26,000 coincidence might prove to be more than coincidence, that the accumulated anomalies might resolve into a pattern that reveals something unprecedented. This is why the Juno spacecraft will be watching, why ground-based telescopes will be tracking, why the scientific community will be paying attention even if most believe the answer is already known. Loeb has suggested that we should search for new satellites in Jupiter's vicinity after the March encounter. If 3I-ATLAS were indeed a mothership depositing technological devices, we might detect those devices as new objects orbiting the giant planet. The signature would be unmistakable. Objects that were not there before, objects that cannot be explained by natural processes, objects that humanity did not create. The probability of finding such objects is vanishingly small. But the search itself costs nothing. The Juno spacecraft is already there. Its instruments are already operational. Looking for anomalies in Jupiter's system is part of its mission, regardless of 3I-ATLAS. If something appears, the discovery will be made. If nothing appears, we will have learned nothing new but also lost nothing in the looking. This is the nature of scientific investigation. You look even when you expect to find nothing, because sometimes you find something, and when you do, the looking was worth every moment of the search. Beyond the Jupiter encounter, the story of 3I-ATLAS will continue in the form of data analysis. The observations collected during this December passage will take months or years to fully process. Papers will be written, models will be refined, arguments will be settled or prolonged. The chemistry that seems so strange today may become familiar as we understand it better, or it may remain anomalous, a puzzle that points to something we have not yet grasped. The James Webb Space Telescope has additional observations scheduled, follow-up campaigns to track how the comet's coma evolves as it recedes from the Sun. Will water become more dominant as carbon dioxide subsides? Will the methanol production rate decline? Will new molecules appear as different layers of the nucleus become exposed? Each question has implications for our understanding of cometary chemistry and the diversity of objects that drift between the stars. Radio telescopes will continue listening for signals. The Allen Telescope Array, the Green Bank Observatory, other facilities around the world. The search for artificial transmissions from the direction of 3I-ATLAS will persist, even as the comet fades from visible observation. The absence of signals to date does not prove the absence of technology. It proves only that we have not detected technology. The distinction matters, and in laboratories around the world, scientists will ponder the broader implications of what we have seen. 3 interstellar objects in less than a decade. Oumuamua, Borisov, 3I-ATLAS, each one different, each one revealing something new about the universe beyond our solar system. The sample size is growing. Patterns may emerge, or diversity may prove to be the only pattern. We stand at a moment of transition in our relationship with the cosmos. For most of human history, we could only observe our own stellar neighbourhood, the planets, the moons, the comets that circle our sun in predictable orbits. We were isolated, provincial, limited to the one example of a planetary system that chance had placed us within. Now the universe is coming to us. Objects from other stars are passing through our skies, carrying chemistry we have never seen, displaying behaviours we are still learning to interpret. Each visitor is a messenger from another world, a sample from a laboratory we could never reach on our own. The isolation is ending. The cosmos is introducing itself. 3I-ATLAS will not be the last interstellar object we observe. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in the coming years. Its surveys will detect fainter and more distant objects than any previous telescope. Estimates suggest we may discover 1 or more interstellar objects every year once the observatory reaches full capability. The trickle of visitors will become a stream, and somewhere among those future visitors might be the one that changes everything, the one that cannot be explained by natural processes, the one that forces us to confront the reality that we are not alone. That day may come in 10 years, in 100 years, in 1,000 years, or never. We cannot know until we look, and so we look, with every telescope we have, at every object that passes through our skies. 3I-ATLAS has reminded us why this search matters, not because it is likely artificial, the evidence suggests it is not, but because the questions it raises connect to the deepest mysteries of existence. Where did we come from? Are we alone? What is our place in the universe? These are not abstract philosophical puzzles. They are questions that science can address, that observations can inform, that data can constrain even if it cannot fully answer. As I bring this exploration to a close, I want to thank you for joining me on this journey. We have travelled from the first announcement of discovery through chemical analysis, X-ray observation, colour transformation, and trajectory calculation. We have considered the possibility that 3I-ATLAS is something extraordinary and the probability that it is something ordinary but still remarkable. We have heard from skeptics and believers, from experts and speculators, from those who see a comet and those who dare to imagine more. The truth about 3I-ATLAS lies somewhere in the data we have gathered and the data yet to come. It will not be revealed by enthusiasm or dismissed by skepticism. It will emerge from patient analysis, from careful measurement, from the slow accumulation of evidence that is the heartbeat of science. 5 days from now, 3I-ATLAS reaches its closest point to Earth, a moment that will pass in an instant of cosmic time, and then it will recede, growing fainter, moving faster, heading toward Jupiter and beyond into the endless night between the stars. But it will leave something behind: data, questions, wonder, a reminder that the universe is larger and stranger than we often remember, that visitors can arrive from impossible distances carrying impossible ages, that somewhere out there beyond the light of every star we can see there is more. More chemistry, more physics, more mystery, perhaps more life. We are children of the cosmos, made of atoms forged in ancient stars, thinking thoughts that no other known being in the universe can think, looking up at a sky full of secrets and daring to ask what they mean. 3I-ATLAS asked us nothing. It simply appeared. It simply passed. But in its passing it reminded us that the questions are worth asking, that the search is worth continuing, that the wonder we feel when we look up at the night sky is the most human thing about us. The comet moves on, the data flows in, the analysis continues, and somewhere in the darkness between here and the next star the answers are waiting. Thank you for spending this time with me. If you found this journey worthwhile, I hope you will leave a like and subscribe to continue exploring the mysteries of the cosmos together. Everything we discuss here is meant to inform and inspire, not to spread fear, not to make claims we cannot support, but to share the genuine wonder of discovery in all its uncertainty and beauty. As always, I remind you that while we speculate about possibilities, the scientific consensus remains that 3I-ATLAS is a natural interstellar comet. Unusual in its chemistry and behaviour, but fundamentally a piece of ice and rock from another star doing what comets do when they encounter solar warmth. The alternative hypotheses are worth considering but should not be treated as established fact. Science proceeds by evidence, not by preference. Wherever you are in the world, whatever time it is there, I hope you carry a piece of this wonder with you. Look up at the sky tonight if the weather permits. Know that somewhere out there beyond your vision an ancient traveller is rushing past. A visitor from another sun. A message in a bottle that has drifted for billions of years to reach us now, in this moment of cosmic coincidence. Good night, and keep wondering.